Very good morning. Welcome you all to the NPTEL course on Advanced Distribution System Analysis and Operation. As of now, we have seen how to apply graphical based distribution load flow algorithm for single phase systems, but in general, the systems are not necessarily to be single phase. More or less, most of the time, it is three phase too. So, how to apply this graphical based distribution load flow algorithm for a three phase system become a new challenge. So, today we will concentrate how to model our three phase system to solve or to obtain the load flow solutions using graphical methods. Three phase power flow with unbalanced DR penetrations. So, we are considering assume it to be a three phase system and it is unbalanced along with DR penetration. So, this is one of the most complex system one can ever imagine in case of a distribution system. Now, there are many challenges with unbalanced distribution system and unbalanced DR penetration. So, we have a three phase system. Normally, we convert into a single phase system and solve it, but now let us assume it is a three phase system which is purely unbalanced, and then we also assume that unbalanced DR penetration do exist in this. So, the voltage imbalance from uneven DR injection shortens equipment life and reduces efficiency. Excess neutral current under unbalanced risk conductor overloading. Protection relay may false trip or fail to detect fault in unbalanced conditions. Unbalanced loading increases phase to neutral losses, lowering overall efficiency. Power quality degrades with increased flicker and harmonics, asymmetric DR output. Inverter voltage Bohr control becomes more complex under phase imbalance. Negative sequence currents from unbalanced stress machines and protection equipments. So, these are the challenges one can commonly experience due to unbalance. And now, let us understand three phase unbalanced distribution network power flow using graphical methods. So, as you could see, this is my phase A, phase B, phase C and neutral, and this is the primitive circuit of a three phase line segment. So, graph theory and matrix algebra can be used for three phase unbalanced load flow analysis. Unlike conventional method, no lower upper triangular decomposition of any matrix decomposition is required. 5 key matrices are transformed into three phase equivalent, path impedance, path drop, loads beyond branch, slack bus to other bus drop and load flow matrix LFM. So, PI, PD, LB, SBOBD and LFM, those 5 matrices need to be determined. Radial network with DGs as PV buses. PV breakpoint matrix computes reactive power injection and withdrawal to maintain voltages. Now, the 5 key matrices are transferred into three phase equivalents. So, try to understand what is loads beyond branch LB, path impedance PI, path drop PD, slack bus to other bus drop SBOBD and load flow matrix LFM. So, to start with, what is loads beyond branch LB matrix, and we consider a single line diagram of a three phase distribution system. So, this is going to be a slack bus and then is going to be the bus number 2, bus number 3 and bus number 4, and 3 and 4 are considered to be extreme. And this is path from actually slack to bus number 3, and this blue one is the path from the slack to bus number 4. The LB matrix identifies all loads beyond a branch in a distribution network. The LB matrix for the distribution network in figure is given by LB, which is SABC 2, 3 and 4. Now, the question here is that in LB matrix, each element is a submatrix of the order 3 cross 1 except scalars, that is except 1 and 0, where SABC is nothing but my SABC for 2, SABC 3 is for SASBSC for 3, SABC 4 is for SASBSC 4. Now, what exactly we like to highlight here, that in case of determining once the SABC for the bus number 2, bus number 3, bus number 4 is known to me, then we can create the LB matrix easily. Now path impedance, that is PI matrix. Before we get into the matrix, let us try to understand. So these three phases are identified with different colors: phase A, phase B, phase C, and we have actually branch 1, branch 2, branch 3, and bus 1, bus 2, and bus 3. So we have a bus 1, bus 2, bus 3, branch 1, branch 2, branch 3, and then we multiplied 3 times to make it as a 3-phase system. The PI matrix identify all branch impedances in each path from slack bus to end buses. The PI matrix for the distribution network in the figure 18.3 is given by PI, which is given in the equation number 18.2, where ZABC 1, 2, and 3, they are 3 by 3 matrices representing 3-phase line parameters. Diagonal entries are self-impedances and off-diagonals are mutual impedances between phases. So ZABC 1 is given by 18.3. Similarly, we can calculate ZABC 2 as well as ZABC 3. Let us move into path drop PD matrix. The PD matrix evaluates the voltage drop in each branch existing in the path connecting slack bus to the end bus. In this matrix, rows represent path under consideration and columns represent a drop in the respective branch connecting slack bus to the end bus. So you can determine the PD in equation number 18.4, where FC is the feeder current and which is represented. FC for 3-phase ABC is given by FC A phase, B phase, and C phase. Similarly, you can calculate FC ABC for second as well as for the third one. Now, what is SBOBD matrix? The SBOBD matrix evaluates the total voltage drop between slack bus to other existing buses in each path of the distribution. So, you can determine SBOBD is given by the equation number 18.5, and each and every element is known to us. From the 3-phase network 18.3 diagram, we can calculate what is ZABC, FCABC, as well as almost ZABC for 1 and 2 and 3, FCABC for 1 and 2 and 3 can easily be calculated, and finally we can have what is SBOBD matrix. Now, the final one, load flow matrix LFM. So, LFM matrix is the load flow matrix. LFM is nothing but U minus SBOBD, where U is given by VABC for the slack bus, BABC for the slack bus, BABC for the slack bus, and finally 18.6 represent the arrangement for your U matrix, and U minus SBOBD will give me LFM. Now, there will be a question between you, actually the 0 elements, which justifies the interconnection relation, which leads to 0, otherwise they are the values of slack bus. A search operation is performed on the LFM for selecting the 3-phase non-null vector, any random vector from each column of matrix LFM, leading to the formulation of a new voltage matrix V nu. Now, moving to 3-phase unbalanced distribution network power flow with the presence of DG, we will see how it can be modeled with the presence of DGs. 3-phase with DG. Mathematical models help accurately represent DG behavior in power flow analysis. Proper DG modeling is crucial for assessing its impact on the system. DG models in power flow analysis includes constant power factor models, variable reactive power models, constant voltage models, and bus classification based on DG power output, PQ nodes, small DG output power, PV nodes, large DG output powers. So, PQ type distributed generators. This type of distributed generations has real and reactive power as the specified values, because sometimes it is PV type and sometimes it is PQ types. Now, how to model PQ type become a question. The power injected by the DG needs to be reflected in the LB matrix of the distribution network by considering injection by the DG as the negative load. So, instead of considering it is a PQ load as a load bus, we consider it as a negative load bus as equivalent to a PQ type distributed generations. For example, consider DG, the distribution network in figure as shown in the right hand side. The modified loads beyond branch matrix will be given by equation number 18.7. Now we can move to PV type distributed generations, where we are connecting two DGs, DG number 1 and DG number 2, and one DG is connected at bus number 3, the other DG is connected at bus number 4, but they are not like previous one PQ type, but they are PV types. So consider a 3-phase radial distribution network with PV nodes as shown in figure 18.5. PV buses treated as generation buses maintain constant real power while adjusting reactive power within set limits to sustain voltages. The net reactive power injection or withdrawal is compared using the PV breakpoint sensitivity matrix. Figure 18.6, which talks about the equivalent single line diagram of the system shown in figure 18.5 for PV bus breakpoint injection calculations. Now, the breakpoint equation called as PV breakpoint sensitivity matrix can be written as in equation number 18.8 as well as 18.9. Further, we can move to equation number 18.9 can be modified to equation number 18.10 with delta V ABC, delta I ABC, delta ABC and delta ABC components. So, this is what we obtain in equation number 18.10 with the assumption of all bus voltages being close to 1.0 per unit and the phase angles are small. The following equation holds good with the following assumption. Further, we can simplify to equation number 18.11 and 18.12. Now, using equation number 18.11, 12 and 10, we can regenerate equation number 18.13, and the above equation can be represented as x minus Rx. This is my x, this is R minus R, and this is going to be x, and this is delta Q, and this is delta P, delta V, and delta delta. So, 18.13 now can be re-represented. So, once we obtain the equation in 18.14, x r minus r and x, delta q, delta p equal to delta v, delta p, all these values are assumed to be from the previous equation, the value of x, the value of delta p, the value of actually r, delta q, delta v, and delta delta. Using the above substitutions, the sensitivity matrix can be reduced to x11 ABC, x12 ABC, x21 ABC, x22 ABC, delta Q ABC, and delta Q ABC equal to delta B ABC and delta B ABC. That is equation number 18.15. The exact amount of injection or withdrawal of reactive power to from the PV buses need to be reflected in the LB matrix of the network. If the computed reactive power infringes on the boundary constraint, then reactive power generated or withdrawal will be positioned or fixed at the violated boundary limit, and the DG will behave as a PQ generator. Remaining matrices will reshape or reconfigure themselves in accordance with the changes in the LB matrix. Therefore, the proposed algorithm is capable of handling various type of DGs. The modified LB matrix will be of the type as you see in equation number 18.16. Now, further we need to determine the sensitivity matrix for a distribution system with a PVB, number of PV buses. The sensitivity matrix or the breakpoint matrix is formulated using the steps given below. We can have 18.17, that is the X matrix. The diagonal entry of X equals the sum of the positive sequence reactances of all 3-phase branches from the substation route to the PV node, and off diagonal elements, that is XK LABC, which is XLK ABC, So there is no shared path, so x scale ABC equal to 0, and for the shared path, x scale ABC is the modulus of the sum of the reactances of the common sections. Now we can calculate the sensitivity matrix, which is x delta Q equal to delta V, that is change in reactive power for each PV bus, and change in voltage at each PV bus can be calculated. So delta Q, delta V, and we can assume that delta equal to 0 and delta P equal to 0 in case of a PV constant voltage bus. And this is a repetition of the same algorithm, graph-based load flow three-phase radial distribution network. You have to obtain the load system data, determine LB and PI, create three-phase voltage matrix V, and then tolerance sigma may be assumed to be 0.001, set the number of iteration could be 100, calculate FC, FD, SBOBD, then calculate the V nu, then determine the convergence, then maximum value of convergence matrix, that is dB max, can be determined. If it is belongs to epsilon, then you exit. If no, then update the voltage iteration. If it is no, then solution does not converge. If it is yes, then you come to this method. If you closely observe, the algorithm across the board remain of the similar structure, excluding changes due to single phase to three phase and integration of D, either it is PV type or PQ type. Now, a couple of case studies are being demonstrated to evaluate the performance of the proposed load flow algorithm in the presence of distributed generations across various standard distribution systems. There are two distribution systems being considered, IEEE 13 bus, IEEE 123 bus system, and IEEE 13 bus we consider DG at bus number 633, and IEEE 123 bus system we consider DG at bus number 9. So every DG is treated as a PV node with fixed voltage magnitude of 1 per unit. Now this is how the modified IEEE 13 bus distribution system. So DG is able to maintain the voltage magnitude at bus number 633 equal to 1 per unit, and DG is integrated at bus number 633. DG is treated as a PV bus with a voltage magnitude fixed at 1.0 per unit. So just to conclude, scalability analysis is carried out with IEEE 123 bus test system. A system size grows up to 123 buses, graphical method computational time scales more favorable, and convergence time remain almost constant. Moderate DG injection up to 0.8 per unit of feeder load raises voltage downstream, improving minimum voltage margins. Excessive DG above 1.2 per unit can cause overvoltage at upstream nodes unless reactive power is properly curtailed. So as you could see, the convergence time for 13 bus it is 0.01 second, and for 123 it is 0.01 second. So almost similar time. So this is the advantages, when the bus is significantly increasing. In case of graph based distribution load flow algorithm, the time is not significantly or exponentially increasing. So this system has been validated with different by X ratios. And what is the reason for fast convergence? So the reason for fast convergence for graphical method against conventional method, this algorithm utilizes simple matrix operation to solve the LF problems of the distribution network. The formulation of the PI matrix ensures a minimum number of such operations to identify all paths connecting the slack bus to the N bus in the distribution network. Also, this matrix provides information regarding the branches existing in each path in minimum such time. This algorithm is formulated entirely on various matrices, formulation and computations, even at the stage of upgrading the voltage at every individual bus. With this note, we come to an end of load flow, three-phase load flow algorithm with DGs, and the conclusion is that especially for large system of three-phase, graphical method for load flow solution seems to be more appropriate against conventional approaches. Thank you.